from Soochow University.
My name is D121
University.
And we will have team to introduce them next year. Start with Flo.
I'm captain of team sales here. My name is D121 PF5, and this is Chen Kuai-Xuan, this is Liu Helong, this is Zheng Zongyang, and this is Su Dao. Thank you.
Hi, I'm the captain of online as well, Taipei American School of Public Health. Well, this is Chairman CEO of Manuel Lee, Senior Training, and LAU.
I'm the team captain of Crusader. These are my team best friend, Chen Wei-Xuan and Wang Zhao. And I believe it will be a great physics debate, last great physics debate with all of you.
Thank you. So because this is round 5, so each team already chosen the topic. So we will have 5 minutes for the reporter to present, to prepare. And please write your presenter's name on the bracket.
Oh, okay. Hey, you guys,
move on to a theoretical model and experiment to find a calculation. So we'll start from this. This is our SO setup. There is of course the ruler and post. And to measure power performance that we mentioned, we need to apply force on the ruler. We use the pendulum. And to measure its release and pace on the ball at the same time, we use the electromagnet to control it. And the tie string is for handling the pendulum. So this is a picture of our setup. And this is a special video. So you can see in this video, when the force is applied, the ball will experience a rapid acceleration, and which is ejection velocity. And what the problem that we want us to investigate is the initial ejection velocity, which is this point. So let's move on to the qualitative explanation. So before the pendulum strikes on the ruler, the projectile is placed in the edge of the ruler. So it will make deformation to the ruler and make the ruler to store elastic potential edge. And how the ball not be ejected is because that in this field condition, when the pendulum theta is smaller than the static friction of a static friction coefficient, the static friction will prevent the ball from slipping out. And the ruler will store potential edge caused by bending. And when the pendulum hits on the ruler, the applied force will make the ruler's deformation increase. So it will store more elastic potential energy. And the frictional force is exceeded by the restoring force of the ruler. So the ruler will snap back, and then the ball will eject. And the overall energy conversion process will be looked like this. The elastic potential energy per ruler will be converted to the kinetic energy of a ruler and also a force. And there will be also an energy dissipation. So let's move on to the theoretical model. We apply the overlapping theory to describe the ruler by its deform. And we will discuss the ruler into two parts. The first part is between the face point and the force application position. And the second part is between the force application position and the contact point of the ball and the ruler. And assuming that we apply force at B, where S is between 0 and B, which means the A is between the face point and the force application position. This part will affect by both the force we apply and also the normal force given by the ball. And when S is between 0, it's between B and the edge of the ruler. This part will only be affected by the normal force given by the ball. So we can get a curvature of the beam by using this formula, which can be derived from the bending moment, Young's modulus, and also the second angular area. And as integration, we can get the deflection of the ruler, which will look like this one and this one. And since we want to investigate this scenario through the energy, so we need to know about the elastic potential energy per ruler. And after integration, after using the formula we derived in the last page, after integration we can get this formula, which is describing the elastic potential energy when the ruler is deformed. And since I mentioned that the energy transition process will be looked like this, we will assume that the energy dissipation is alpha times the elastic potential energy. And alpha is the ratio of the energy dissipation. And the ratio of the kinetic energy between the ruler and the ball will be equal to beta times the ratio of the elements. And we'll apply the alpha and beta, which are the constant by our equilibrium. So after this formula, we can know that the ejection velocity will be looked like this. And to get the constant alpha and beta, we mentioned in the last page. In our student data, we found that the percentage of the energy converted to the dispersion is will be roughly equal to 0.48, which is this chart. And the chart on the left, on the right, shows the ratio of the kinetic energy of the ruler and the force. And we can use the slope of the straight line to get the beta. And we found it will be roughly equal to 0.04. So let's move on to the experimental analysis. And this is the first parameter we do, which is the strength position of the pendulum. And the further away the strength position is from the face point, because different strength position will cause the ruler to have different bending moment, and it will cause different elastic potential energy. And the further the more the elastic potential energy the ruler will store. So it will also make the ejection velocity too fast. And about when the strain position is very close to the ball, there will be a deviation from our zero line and the data. We will talk about this data. And this is the second parameter we do, which is about the pendulum release height. And different pendulum release height will cause the magnitude of the force we apply on the ruler. And we will obtain the force magnitude by check the pendulum's initial and rebound velocity, and also contact time of the ruler and pendulum. So we found that when we apply a larger force, the ruler will store more elastic potential and causing the ejection velocity will be higher. And we also found that with a larger force, the minimum velocity will shift to the left, just like what is chart. And about I mentioned that when the striking position is very close to the ball, there will be a large deviation from the external data and the series line. And why this will happen is because that when it's very close to the ball, like the striking position is very close to the ball, the space for the ruler to deformation to have a large deformation is not enough. So the energy conversion ratio will decrease significantly. So which means the ejection velocity will also decrease. So this is why this will happen. Just like this. And we also do the measurement of Young's modulus. We use the force gauge to define the ruler and measure the corresponding force. And by plot the force and the deflection into the class, we can use the slope of the straight line to calculate the Young's modulus and also the second actual moment area. To calculate the Young's modulus, and we can measure the second actual moment area by using the formula. And this is the last parameter we do, which is about the material of the ruler. And when the applied force is fixed, the ruler with a smaller Young's modulus and second actual moment area will store more elastic potential energy, and it will making the final ejection velocity too fast. And in our experiment, we found that the aluminum ruler's Young's modulus times second actual moment area will be larger than that of the iron ruler. So the ejection velocity will caused by the aluminum ruler will be larger than the iron ruler, just like this chart. So let's move on to the discussion. So since we use the pendulum to apply force on the ruler, it will have a boundary condition. We found that in our experiment that the ejection will have three different conditions, which are the successful ejection and failed ejection, and also vibration. And in this video, you can show that you can find that the ball is not ejected directly because of force we apply on the ruler, but it's because of the vibration of the ruler. And this video shows the condition, shows how it will look like when the ball is failed to eject. And this is the second boundary condition we observed in our experiment, which is about effect operation. And we test for different materials, which are dusty, iron ruler, and check for tracing force and the plain paper. And how we do this experiment is by wrap the item around the projectile, and find out that the boundary condition will shift to the left with a bigger force, and the ejection velocity will increase with a smaller static friction coefficient because the conversion ratio will increase. And we also found that when we apply uneven force to the ruler, it will have a very interesting phenomenon. The ball will tend to eject to the side where less force is applied. And we create an uneven force by adjust different release height of the pendulum in two sides. So the ruler will tend to eject to the side with the 13 centimeters. And we also found that the ball will self-rotate when it is ejected. So let's move on to the conclusion. So how does the energy transfer through the force ejection? And this equation shows the overall energy conversion process in our experiment. The elastic potential energy of the ruler will be converted to the kinetic energy of the ruler and the ball. And there will also be some, and there will also some energy dispersion. And we can fit the ratio by using our data. It will be roughly equal to 0.48. And we can use this formula to describe the elastic potential energy stored in the cooler. We're going to apply force on it. And how does the apply force contribute to the ejection velocity? The further away the striking position is from the ball, is from the face point, the faster the ejection velocity will be. And the higher the bigger the force we apply on the cooler, the faster the ejection velocity will be. And the smaller the Young's modulus times the second edge of normal area, the faster the ejection velocity will be. And we also found that there will be 3 given conditions in our experiment, which are the successful ejection and failed ejection, and also vibration, which are shown in this chart. And these are the boundary conditions in our experiment. Thank you for listening.
Alright, so I'd like to ask you a couple of questions first. When the ball is in motion in the air, does it spin like after it's been launched?
No.
It doesn't spin. How do you make sure that it hasn't spun?
We will check the motion of the ball, and we will find out it's not spinning.
So, okay, so the ball when after it's being launched, it just bounces perfectly.
Only when the force we apply on the 2 sides only then the ball will rotate. But the force we apply on Lura is uniform, so it will not rotate.
Okay, so when the force is uneven, then the ball spins, right? So how do you account for the torque, like when the ball is spinning, when the force is uneven?
But in our experiment we mainly focus on when the ball is not rotating. Like.
Okay. Further on, earlier in your slides, you talked about how you subtracted energy dissipation in your calculations, right?
Yes.
So how do you calculate energy dissipation?
We will obtain the energy dissipation ratio by using our data, like the we will compare the elastic potential energy per Lura and the kinetic ratio of the ball.
Okay, so for moving on, you see in this graph over here, can you explain how you got like this line to like this set of data? Because right now it looks like it's kind of oscillating, and are you sure that like this line like really like fits that data? Or
This is just a small deviation.
okay. So when you calculated this,
We'll calculate the kinetic energy per Lura.
okay.
And also the pulse. And we will add them to each other, and we will find out the total kinetic energy, and also compare it with the potential energy, and we can get the conversion ratio.
Okay. So why do you think that like there's such like a difference between the potential energy?
That's all.
Alright, so I'm Alright, and I'm going to be opposing ruler cannons from all neighbors. Right, so here's the point statement, and our model of investigating this is first by observing the forces involved in the ruler cannon and determining like the overall trajectory of the ball. Then we calculate the theoretical model using the strain energy stored in the bending rulers as well as energy loss. Then we investigate different parameters such as the distance from the fixed point or the magnitude of the force and how that affects the energy of the ejected ball. And then at the end we follow with conclusion and error analysis. So our opponents, they started with some preliminary experiments talking about ball acceleration as well as investigating static friction. Then we moved on to the theoretical model where they talked about strain energy stored in the ruler while it's bending as well as the Euler-Bernoulli beam theory. And then we moved on to experiments and data where they talked about how different parameters affected the results as well as finding Young's modulus and finding boundary conditions for success and failure. So some pros, they had a detailed experiment set up, they detailed how they derived their theory, they have a clear conclusion, and they explained how the parameters affect their results. Some cons include how they have an unclear method for data collection, there's a little explanation of the physics concepts and behavior of the cannon, there's unclear explanation of the graph shape and data points, and there's a lack of error analysis. So a couple of things that I would like to discuss for a discussion later. First, I'd like to talk about the spin of the ball, like when it's going through the air, or the spin of the ball before it leaves the rulers. I'd like to talk about the graphs and like get more explanation on like how they work and how the line fits the data. I'd like to talk about lost energy, specifically about the discrepancy between potential and kinetic energy. And finally, I'd like to talk about just like various sources of error that might not have been accounted for. Right. So first, can you go to page 26 of the slides? Right. So here we have like this graph where we're talking about different boundary conditions. So first, we have like these lines that we see.
We will test like every striking position and different height of release pendulum. So we will get the exact condition like when I strike with it is 2 and the height of release pendulum is maybe 0.5. We will know the condition and we test all of these conditions and we will drop it into the curve.
So you guys tested like all of these different combinations, right?
Yes.
Okay. Well, about like the lines specifically, how did you know like to draw the lines here? Or
I'm just showing the area.
okay, okay, cool. Next, I'd like to talk about the ball spinning, specifically like when the force is uneven, for example. So when the force is uneven, like does that why is it that the ball moves to the side where the force works less?
Because when the force on the two sides not the same, the side will have the larger magnitude of the force will have a bigger effect on the force velocity, so it will tend to eject to the side where less force is applied.
Yeah, that's the sign.
Like when the force maybe here is 5 Newton and here is 3 Newton, and in this side the force will affect the ball's velocity more. So the ball will tend to eject to this direction.
Another thing that I was wondering about the experiment setup was that after the ball gets ejected, is it touching the ground like after it leaves?
You want to touch the ground.
It's not touching the ground.
Yes, we measured that the ruler and also the ball will not touch the ground.
Okay. So in this experiment setup, how many camera angles did you use then? Like, is it just this one we see here?
This one and also this one. We will use this camera to check the velocity of the ball.
Okay.
And also we place the camera here to make sure the ball is not spinning. When the ball is not spinning, it will cause a kinetic energy.
So the ball isn't touching the ground. How do you like account for like any potential 3D motion that it might have?
Because the power signal only want us to measure the initial ejection velocity, so we don't need to actually calculate. Like the force when it is the velocity when it is go maybe here or here. We only need to know about initial velocity.
Okay. Okay, so moving, wait, so you only calculated the velocity of the ball like right after it ejected, right? Is that
Yes, like in my oscillating video. And we find out that because when the ball is ejected, it will, like here, when the ball is high, it will have a large acceleration. So we only need to investigate this point, which is the initial ejection velocity.
okay. Okay, so moving on. When we talk about the energy that's being transferred from the ruler to the ball. Wait, so you know how like the rulers, they don't fully clasp, like they only like go together after the ball leaves, right?
Yes, they will connect to each other.
Okay, but so are you saying that like so according to your data, do the rulers like do they go together after the ball leaves, or do they go together like right as the ball goes?
When the ball leaves the ruler will go the ruler directly connect to each other.
So like does it like
We will calculate the kinetic energy when the ruler is connected to each other.
okay? So how do you go from like how do you account for like that error how do you account for the error, because like the rulers aren't like fully clasping back together on the ball itself, right? They're clasping back together after the ball leaves, right?
So I mentioned that the elastic tangent energy, which is the original one, it will be transferred to the kinetic energy of a ruler, which is the collecting velocity, and also the ejection velocity of the ball. It will cause the kinetic energy.
So this energy that you're talking about in the ruler, is it stored throughout the ruler, or is it like only in the part that bends?
It's throughout the ruler. Like when you apply force to the ruler, it will have a more deep. It will cause the ruler to have more dimension, so it will store more elastic potential energy. And potential energy we calculate is the is split.
Okay, so you're saying, so when you calculate, so can you talk about how you calculate the kinetic energy of the ruler? So like, do you take the mass of the whole ruler, or?
Here. We use this formula to calculate the kinetic energy of the ruler.
Okay, so wait, here.
Yes.
Okay, so can you okay, so can you explain how? Okay, so in this experiment, you also talked about how you calculated Young's modulus. Right? Can you elaborate on how you calculated Young's modulus?
Calculate Young's modulus.
For the rulers.
We will first use the force gauge to deflect the ruler, and we will measure the corresponding force, and we will plug it in this chart. And we can use this formula to calculate the Young's modulus. And L is the length of the ruler, and this is a constant, because we can measure the second edge of movement area by using his formula, which is B times H 3 times n divided by 12. And we can use the formula to calculate the Young's modulus, because we have the ratio of the deflection and also the force. This is the deflection, this is the force.
Okay. Okay, so another thing about the graphs is that can you like notice some of your graphs about like how the different parameters will affect the exit velocity? Like how like the parameters affect how different parameters will affect the ball as it goes out.
We mentioned in our experiment that the striking position and also the force we apply and also material of the ruler. These three. Yes.
Okay, so how did first of all, I want to know how you calculated these error bars that we see.
This is because we do the experiment for many times, and we will find out the average ejection velocity and the other likely deviation between this data will become error.
Okay. So like okay, so you did multiple trials to find like these error bars.
What do you mean?
Okay.
Because I have do this for many times.
Okay. Okay, now let's just go back to the part about field. Specifically, I how do you know that like all of the elastic potential energy is converted to kinetic energy? Or do you not?
I didn't say that all of the elastic potential will convert into kinetic energy. There will be energy distribution, which is alpha times the potential energy per the group. And we will fit the constant alpha, which is the ratio of the conversion by using our data.
Okay. Moving. Okay. So you calculate the excess energy in the ruler like after the ball leaves through the equation that you mentioned earlier. Right?
So we can say
Like the excess energy in the rulers after the ball has left.
yes, after the ball left from the ruler, if the ruler still have a kinetic energy because they will be connected to each other.
Okay. Now I also want to know about this part. Like here, for example, when the rulers are going together but the ball hasn't left yet. While it's here, does the ball like rotate like in the ruler here?
No, it will not rotate because we apply the force at the center of the ruler, and also we place the ball on the center of the edge of the ruler, like these points. So we'll make sure that the force is uniform in all the directions, so it will not rotate.
Okay. So so you're saying that the ball doesn't rotate because the force are equal.
Yes.
Okay. Also, another parameter that you used was compare the two rulers, right?
Yes.
An iron and steel ruler or something. But so the main difference is like the stiffness of the Young's modulus of these rulers, right?
It's a material part.
Okay. Did you account for like the difference in friction that these two rulers might have?
Yes, we consider it in the boundary condition.
Wait, sorry.
We consider it in the boundary condition. Like the ruler with a smaller static friction coefficient will can eject the ball faster.
Okay. How did you calculate like the friction that the ball would face like between the two different types of rulers?
Do you mean the static friction of the kinetic friction?
Which are the standard friction.
We will place a ball on the ruler and measure the angle that the ball was starting to go up. Like this is a ruler, and we will change the ruler from here to here, like this, and we will find an angle that the ball started to go down.
Okay. Well, how about the kinetic energy? How about the kinetic friction that the ball faces, like between the two rulers?
You mean how do I measure it? This is the there is a formula for the kinetic friction coefficient, but we didn't put it on the PowerPoint. And we will use the formula to calculate the exact kinetic friction coefficient of the ruler and ball.
Okay. Okay. So about the Okay, so here in this diagram, I can see that you labeled it the force one from like center of
The first one is the normal force given by the ball to the ruler.
Okay. And how did you calculate this normal force?
What calculate the normal force?
Or
There's a formula that is describing the deflection and the differential of the ruler and also the force. And we can use the formula to cancel.
Anyway, so I'd like to summarize our discussion. So first, we talked about how the lines, how they determine the different lines on their boundary conditions for their graph. And our reporters said that they did a lot of. They said that they did all the different trials and tested the areas. They talked about how. They also talked about how the rulers, how the ball does not touch the ground right after it gets ejected, and they talked about how they only account for the initial velocity right after the ball gets ejected, not like the velocity while throughout its traveling in the air. We talked about next camera angles. They said that they used the bird's eye view to calculate to be able to track all of that. The next on the topic too, they said that the ball ejects the side with less force because the ruler gets big. They said that the ball ejects the side with less force.
However, I will ask for the reporter, and I want to ask, do you think the young module will change?
The Young's modulus is the property of the material. So if the material is the same, it will not change.
It will not change.
Yes, with the same, maybe a set will not change.
What do you think?
Well, I agree because the Young's modulus is a property of
Yes,
the material.
will change or not?
Wait, what do you mean? Like change between different materials or?
Young's module, the number of Young's module will change or not?
From the same ruler now.
Same rule now, okay. I want to ask for a reporter, and I'm sure that you release in the same parts will have the same force.
Yes.
Yes. Okay. And also I have seen that. Do you consider that your extra force can connect the ruler in the same time?
Yes, because we use the electromagnetic control, so it will use the ruler basis.
Okay. And I also want to ask for opponents. And so you focus on the spin. So do you think the ball will rotate?
Well, I think that there could still be a little bit of spin in the ball itself, and that can create like some torque while the ball is spinning. And so I think like maybe we can like look at that and turn it on.
So you think that it will also have a small speed?
Yeah.
Yeah. Okay. And how do you think that if you will have a spin, and how do you affect the ball?
Well, I think that spin could potentially could potentially like cause friction, or it could affect the torque of the ball, which will like change it, which will like affect the energy of the ball and affect the velocity.
Okay. I also want to ask both of you, and what kind of energy consumption in ruler energy?
Energy consumption,
Yeah.
the elastic tension energy of the ruler. What do you mean?
Maybe the magnetic friction or.
There will be the elastic tension energy of the ruler, and also the kinetic energy of the ruler and the ball.
Okay. What do you think about it?
I think that like the kinetic energy of the ruler will be converted. The elastic potential energy will be converted into energy of both the ball
So you
and
think
of
it's
the ruler
the
itself.
kinetic?
Sorry.
So you think it is a kinetic?
Yeah, and a little bit gets converted to sound.
Okay. our team is Cassandra and I'm from National Zapa Senior High School, and today I will review the topic is lubricator. And this approach tools tightly held against each other and around contact and is inserted between the close to one of their ends, and when extra force is exerted on the surface, and we will focus on eject at a high speed and investigate the effect at the parameter and at the ejection speed. And we will also investigate the transformation of the energy velocity and the parameter of the effect of the ejection speed. And this is the overview for the reporter. And the phenomena is the tools tightly hold against each other will let or eject. And the experiment is a person to exert force and striking positions and release height and striking point to disclose the transform differently and material of the ruler. And the theory is the friction form is bigger restored and the energy and failed and successful and ball will rotate. And the reporter has a good setup and totality and show complete theory and has experience with design good time management. But I think it is that goes some explanation of the chart like the triangle and that chart. And this is an overview of our opponent, and I think clear to the problem of the project and clear demonstration of the problem itself and adequate discussion of on each problem. But I think it's been too much time on one question of the measurement and to focus on the chart more. And this is the discussion. And opponent does his spins to the reporter, and the reporter said that in their setup it wouldn't if the heights are the same, and also opponent asks if it is rotation, how do we calculate the torque, and reported that that's not our focus. And also our opponent said as why if the force on the two sides is not the same, it will eject all their directions, and reporter said because the bigger part will give the other direction to make it face the direction. And also opponent is about the state differential calculation, and the reporter said he explains the way he calculated. And also opponent is over is the velocity points you calculations, and the reporter said these are the highest points. And also, and we also have asked how to make sure it's at the same time, and reporter said using the electronic device, and we think the same time is important because it will let there are a difference for us. And we also asked about how do you think about spin and will spin and we also asked about the Young's module if it will change. And both of them said no, it won't change, but we think that the Young's module will change in the process. And this is all my review.
So let me get the concrete result of my report. The ball does not spin only when the force effect are uneven, the ball will spin. But our instrument can perfectly control the force is uneven. It is precisely and also the same. So the ball will not spin. And the energy dispersion is being calculated by the kinetic energy. And also the conversion ratio is well calculated in our report. And the calculating is done by using tracker. And potential energy will not fully transfer into the kinetic energy to the ball. But we have used the energy transition ratio, which is the alpha, to get the energy loss. And the reporter has measured the static friction within this room. And the reporter used the electromagnet in order to ensure that the two pendulum unit is released and will hit on the ball at the same time. And also make sure it is uniform. And we have test area striking position and the height release to know about the boundary, which is the chart that has 3 different regions. And review mentioned that the reporter did not explain the chart. However, the reporter has put the serial line and also external data in the chart. And also we have analyzed the error, like why will the serial line be a little bit higher than the data. And also the Young's modulus will remain the same because of because it's a ruler's property. It's a material property. So with a set ruler, it will be less. So thank you for listening.
Okay. Questions from the group?
I have a question of all three of you. How do you think the mass or the size of the material ball will affect the ball?
You mean the mass of the ball?
The mass, the size, and the material.
Different mass of the ball will cause the initial velocity to be different because we are calculating the kinetic energy, and with the same kinetic energy, with if the mass is bigger, the velocity will be slower, and the material of the ball will affect the static or affect the freezing coefficient between the ruler and the ball. So it will make the boundary to be different, and also it will affect the energy dissipation ratio. And the ball size, different size will cause the bending moment to be different because if the radius of the ball is 2 or 4, the dimension will be different. So the ruler will store maybe more or less if that's the potential energy.
And you only use one ball. If you didn't check this thing.
Yes.
And so I think the thing the mass it will change the velocity, and because according to the formula they have, and if the mass will be bigger, and I think the velocity will be bigger, and also the diameter of the ball, and I think because if they have a bigger diameter, and the ruler will flame, and so I think it will change the velocity, and also the material. I think if the material is tough, and it will that is have a more big friction between its ruler and the ball. So I think that the velocity will be lower.
I agree with most of these explanations on how this will affect the ball. But I think the reporter, maybe they should do some more experiments, like changing the ball itself to see if it's true, or to see if like other different stuff will happen to the ball.
I do have a question for you, obviously. How do you judge not to consider the friction force from the table? When you measure the velocity.
The friction force
Yeah.
between the ball and the ruler.
And table.
Table, because we measure that the ruler will not touch the table. So I think the friction between the ruler and table will not affect the velocity of the ball. And the friction between the ball and the ruler will already mentioned in the boundary. Like with the bigger static friction, the ball will decrease the ball's velocity, and also the boundary condition, like when the ball be ejected, is also will also be different.
Do you mean how the table friction affect the ball?
Yeah.
I think the friction between the ball and the ruler, you will let the experience to how to do so. We also will let not compare to the table, and so in this way we can ignore it.
I think that if there's friction between the ball and the table, it might cause some spin as well. Maybe the ball didn't land perfectly straight. Maybe like it landed at an angle or something, which would cause it to spin, which would affect the velocity, and it would change the torque of the ball. So I think that should also be factored.
I have a question. Reporter, could you turn to the page you show the velocity and the striking position? The data, yeah, this one. Yeah. So this one. So my question for the opponent is that you see some data points lies above this theoretical line. You know what happened? Can you guess what happened?
Well, I think.
from their data.
Okay, so I think that these data points, I feel like what they did was that they tried to get some sort of polynomial equation in to be able to fit the data as best as it could. Like I think they like made a recent like program in order to try that, but I think it's like very unclear because we can see that like a lot of the data points don't match up. So I think like maybe so I think like while they tried to get like the line of best fit, it doesn't really work as well.
Review, how about review? What's your opinion? There's some data lies about the theoretical line.
And I also agree with the opponent said, and I also think maybe it is maybe it have a it and the different process between.
How about reported? What's your explanation?
First, I want to clarify that this is not a fitting line, this is a serial line, because we mentioned that the ratio will be, the alpha will be 0.4x, so we can draw this line by using the formula and also ratio. And I think that why will there be some deviation is because that deviation is because that maybe with different rule, there will be a slight change in the alpha, so maybe it will change a little bit.
Okay. All right. Juries. Five, seven, six,